Chances are you've probably never heard the name Shunichi Amari. But here's the thing. You interact with his life's work pretty much all day, every day. He's one of the true architects, one of the people who built the very foundations of modern AI. And his entire career, everything he did, was driven by two huge questions. And if we want to understand the AI world we're all living in, well, we've got to understand those questions. So here's the first one, and it's a big one. He looked at the human brain, this incredibly complex, kind of messy biological thing, and asked, what if we could unravel its secrets using math? Could we actually describe how our own minds work using the clean, elegant language of mathematics? Okay, and then came the second question. And this one is even more mind-bending. He wondered, what if information itself had a shape? What if we could stop thinking about data as just a bunch of numbers in a spreadsheet and start seeing it as a landscape, a geometric space with mountains and valleys? Seriously. These two incredible quests, right there, they're what defined his entire life's work. All right, so let's dive into that first big challenge. This was Amari's quest to build a real, theoretical model of the mind. And you have to remember, this was way, way before AI as we know it today even existed. Okay, so back in the late 60s and 70s, think about that for a second. Amari started publishing these papers that were just completely decades ahead of their time. And we're not talking about just some fuzzy, abstract ideas. No, this was the hard stuff. This was the mathematical bedrock that modern machine learning theory is literally built on. And what he came up with was this amazing framework. Basically, he laid out the blueprint for how an artificial network could do three things. First, learn from data. Second, figure out how to classify patterns in that data. And third, evolve and adapt based on what it learned. Now, does that sound familiar? It should, because that's pretty much the core principle behind almost all AI today. So where did he get this idea? Well, he went straight to the source, the brain itself. He actually used ideas from statistical mechanics, a field of physics, to model how all these massive, seemingly random networks of neurons in our heads could actually process information. This wasn't just a thought experiment. His work created a theoretical basis for understanding things like how we form memories, and it directly influenced the tech we use every single day, stuff like recurrent neural networks. Okay, so that was his first quest. Now, let's switch gears and talk about his second quest, which was maybe even more radical. This was his mission to give shape to the totally abstract world of information. And believe me, this is where things get really, really interesting. To do this, you had to completely change how you looked at things. See, traditional statistics kind of looks at one model or one data point at a time. Amari said, forget that. He asked, what if we could map out the entire universe of all possible models as one single connected landscape? And he gave this new field a name, information geometry. He literally created a whole new mathematical language. He used the tools of geometry, shapes, curves, distances, to analyze this landscape of probability. And why is that so powerful? Well, because it means you can actually measure the distance between different models. You can find the shortest, most efficient path from a really bad explanation of your data to a really, really good one. Okay, I know what you might be thinking right now. This all sounds super abstract, right? Like pure math. But the amazing thing is, this theory led to some incredibly powerful, super practical applications that completely changed how AI learns to solve problems. So in 1998, he introduced this idea called the natural gradient method, and it's pure genius. Because it understands the shape of the problem, it can find the absolute most efficient, most direct path for an AI to learn. It's just a smarter, faster way to get to the right answer. And this is the perfect way to picture the difference. Imagine you're trying to climb a huge mountain, but it's completely covered in fog. A standard learning algorithm is just kind of wandering around, taking this long, slow, winding path, hoping to find the top. But the natural gradient method, that's like having a map and a compass. It shows you the most direct, smartest path straight to the peak. And the impact of this way of thinking has been, well, it's been enormous. We're talking about everything from training neural networks way faster to creating algorithms that can pull a single voice out of a super crowded, noisy room. It's even led to big advancements in things like quantum information theory. Amari's information geometry really has unlocked all these new possibilities all across the scientific world. So when you step back and look at it all, what's the big takeaway from Amari's lifelong journey? Well, to really put his career into perspective, you just have to look at the timeline.
He was born in 1936. I mean, let that sink in. His work has spanned almost the entire history of modern computing. He was figuring out the theory behind AI back when a single computer took up an entire room. It's just incredible.
And please, don't think his work is just history. These aren't some dusty old theories sitting on a shelf. They are alive, and they are actively shaping the future of AI right now. He continues to be this absolutely indispensable figure in the evolution of AI, and is still pushing cutting-edge research forward.
So that leaves us with one final thought. You see, Shun Amari didn't just contribute to AI. In a very real sense, he built the roads and the highways that today's researchers are traveling on. He gave us a totally new way to see information, a new language to describe it. And the big question for all of us now is, on the path that Amari paved, what will AI achieve next?